So welcome all. This is Vic 6 tutorial on the topic Introduction to Machine Learning taught by Professor Sudeshna Sarkar. I am Pintu Kumar. I am a PhD scholar at IUR IIT Bombay. Today we are going to cover topics on deep learning. So this module is related to deep learning. So the topics that I plan to cover are perceptron, then moving to multilayer perceptron, which is commonly known as feed-forward network, or the most common form of deep learning that we encounter today. Next, I'll make some comments about how to decide upon the output layer of a feed-forward neural network. And then I'll mention some of the advantages and disadvantages of different activation function. What is the activation function? You will know in a while. Probably you all have seen the lecture. You already know what activation function is. And in the next session from 7 to 8, Manak is covering backpropagation in detail. He'll talk something about CNN filters, and then he'll try to code this feed-forward neural network from scratch. So if anyone is interested over there, the person can join. So first of all, most of you, like if you have joined the course, you would have encountered some application of deep learning or the other. So the journey of deep learning began with the problem of handwritten digit recognition. So like it started with they had a postal service. So they wanted to read the PIN code from the envelopes that were there. So they wanted an automated program that can read out the PIN code for them. So it all started with them there, and like we have many applications today. So one of the major application is major or the earlier application is to read the handwritten digits and predict what the digit is. One more application is object recognition. So like if you are given a figure, you have to recognize which object is present. So I want to play a small video over there. I'm not sure if sound would be audible to you or not, but yeah, I'll try to play a video. This is a framework called YOLO. So YOLO is full form is you look only once. So it is an object recognition algorithm based on CNN, right? So this is based on CNN, and like it looks at the object only once and try to predict what the object is. I'll just play a video to motivate like this example. Okay, I'll move to YouTube. Just give me a second. I'll play this video.
Could you post that link in the chat box so that we can
I'll
access
post.
that one?
I'll post.
Thank
I'll
you.
post. I posted it, but I'll play it also for you so that it ends at the same time for everyone.
Monsoon invites various problems. Trust Gross in 650. Starts releasing in 5 minutes.
प्रोग्रामिंग में आप कितने प्रोफिशिएंट हैं?
गुड सर.
So it is an object detection. You can see that the object is getting detected in real time, almost with no delay.
I get strung up from a loving. I wish she'd care to see, but she only cares when she's got the time. And I fret so much about her loving. I wish she'd let me be, but her destiny's got us intertwined. And is it really my fault?
So you might notice that all the predictions are not correct. So this eagle is being predicted as dog and
Wearing the jacket I bought.
so this is an example of like how deep learning is useful in these days. So like deep learning is a useful tool to have these days. This is a machine learning course, so there was only 1 week session on this, but like people who are interested can join a specific deep learning course later on, probably next semester. There are few courses on NPTEL which are very good. So other like application is action recognition. So like from the picture you have to like detect what the person is doing. Okay. Another one is machine translation. So you all might have used Google Translator. So that also uses a form of deep neural network. Yeah. So earlier they were using RNNs. These days they use transformers. So, and there are many more applications. So all these are like initially based on something called perceptron. I'll try to explain what a perceptron is. So what a perceptron is, so it's a unit which comprises of two parts. Okay. So like every other machine learning model, this will also have some training data and testing data. It will have some inputs and it will give some output. Okay. Now, let's say one of the training data is of form x1 to, let's say, x4. These are features for this single training data. This is only one data point with 4 features in it. So let's say it is a price of a house prediction model that you want to build, then it is probably the area in which it is located, the area of the plot, number of bedrooms, or those kind of things. So what you want to input these features. So these 4 lines that you're seeing, these are input to this perceptron. So it is x1, x2, x3, x4, and it gives you some single output. Okay, so the output is only one for a perceptron. So it has 2 components. What it does is, first of all, it does a summation, or it is called you like in linear regression, what you used to do is wi xi, I from 1 to 4. This is what you would have done in linear regression. So similar thing we do in perceptron also. So what we do is, first of all, we add them weighted with a weighted addition of these features. So we do x1 w1 plus x2 w2 and x3 w4. Then whatever we have obtained, let's say we obtained z as summation wi xi, we pass that z via an activation function, which is denoted by phi. So phi, then we pass phi this z to an activation function to obtain the output. For example, your activation function can be something like sigmoid. So it will give you 1 plus e to the power minus z. Or it can be your thresholding at 0. So if your like z is greater than 0, then the phi of x is 1, otherwise it is 0. Okay. So these kind of activation functions we use for like a perceptron. This is also called as a single neuron. Why it is called neuron? Because it was motivated by our neural structure of our brain. So in our brain also, many neurons are connected to each other. So they receive some information, they do some computation, and then they output that like whatever result they get. So like now, let's say this. If you have a single neuron, if you have a single perceptron or a single neuron, they always learn a linear boundary. So if you look at this summation expression, so this is always a linear boundary that you would be able to learn out of it. Okay, this is one thing. Another is, let's say if you have some classification task. This is a classification task. Then if you have data points of form xi and yi, right? Then like if like you pass this, let's say this f is the denotion for your perceptron. So if you are passing x to f, what are you doing? You are first taking the summation of form wi xi and then passing it to a like activation function. Both the function composed together, I'm denoting it by f. So if you are getting f of xi as y hi hat, then like how to learn the appropriate w is the question. Okay, so like in linear regression, you wanted to learn the appropriate weight based on your like just a second, yeah, based on your like training examples. Here also we want to learn the appropriate weight functions for this. Now what we want, like what a general update rule over here is, so like if you are w at nth step is wn, then at n plus 1 step you can update it this way. Okay, for every data point you can keep updating till the time it converges. By converges I mean like it is the best separator that you have got. Now there is a like proof theorem that says that if your data set is linearly separable, then you can separate it just using a single neuron. So the one thing to appreciate over here is, so if you look at something like a linear regression, then what you had to do is, first of all, you had to define some sort of loss function, and then use some gradient descent to compute its weights. Okay. Then you would have like converse to some line that separates some linearly separable data points. But here, by just simple computation, like it is much simpler here to compute this thing rather than computing gradient. So by much simpler computation, we are able to achieve the same performance over here. Okay. So just to make these things more like concrete, here is an example. So this is a single neural network. Whoever has raised the hand can please speak or type it in the chat box. So Rahul Sriram, can you please speak?
Probably the mic is not working.
Oh, okay. You can type it in the chat box also. Like whenever you type, we'll try to address whatever you're trying to say. We'll move. Yeah. So this is a single neuron, right? So we want to learn this weights so that this function is able to act as a AND function. Okay. So all these x0 and x1 over here are our Boolean entries. So like if anybody knows, like if my x1 and x2, then what is formula for x1 and x2? So it is 1 1 0 0 1 0 0 1 0. So if both my like entries are 1, then I get 1, otherwise I get 0. Okay, this is what an AND is. So we want to mimic this thing via this neural network, that this should be able to give us the output accordingly. Okay. So they have asked like B1 is equal to 1 is the bias that is also given to us. Okay. So this is B1 is equal to 1. So what should be our W0, W1 and W2 so that this gives us this thing. Now over here the threshold is on 0. So if the output we are getting greater than equal to 0, so the activation function for this neuron is such that if we are getting greater than 0, then the output is 1, otherwise it would be 0. Okay. So now let's see what options fit in over here. So if we look at our first option, so it says that W1 and like every entries is 1. Okay. So let's look at this option. I'll remove the unnecessary markings over here so that it is clear. Yeah. Rahul, you can type it in the chat box if you have anything to ask. Okay. So we have all the entries as 1. So let's see, we are passing x1 is equal to 1 and x2 is equal to 1. Let's take this example. Okay. So what would happen is, this would be 1 times 1 plus 1 times 1 plus 1 times 1. What would we get? 3 over here. Because it is thresholded on 0, what is the output that we'll get? We'll get 1. So for this case, it is being satisfied. Okay. Now let's say for 0, 0 case, you will get 0 over here, 0 here and 1 here. So 0 times 1 plus 0 times 1 is 0, plus 1 times 1 you will get again as 1. So this value is 1 and 1 is greater than 0. So the output you should get via this is again 1. Okay. So you will again get 1 over here, which is not correct. So this option is not correct for us. Rather than looking at every option, let's see how we can find a accurate value of this thing. So what we want is, like if both the values is 1, we want it to be greater than 0. If any one of them is not 1, any one of them is not 1, then we want it to be 0. So this B1 can play a very vital role over here. So if we assign it as something as negative, okay, right, and then this is for AND, right? Yeah. If we assign it as negative, and then we take both the quantities as, let's say, one of them as, let me see. So if we take both the quantities as 1, what do we get? Like for this case, it would be 1. So 1 comma 1, this if we pass 1, 1 to it, so it would be 1 plus 1, 2 minus 1, 1. So it is thresholded, so it will give us output 1. And if we take one of them as 0, then we will get only 1 from these two entries. And then minus 1 will make it 0. And 0 will be mapped to 0. So for both these cases also, we'll get the correct answer. And again, if we have 0 entries over here, we'll get minus 1 as an output, which is definitely less than 0. So we'll get 0 again as the output. So our B option is the correct option. Okay. So this is how we can by brute force, we can look at what the weight should be. But like if you would have plotted it in a two-dimensional figure, you could have started with some random W, then use this update rule, and you would have landed up with the same separating line or any other separating line, but that would have definitely separated this thing for you. Okay, so like weights, different weights are possible, like for a same data set, but you would have landed at some weight. So again, our network is same. So we have something like this. So this is W node. Yeah. This is W1. This is W2. This is X1, X2, and this is B equal to 1. And we want to learn the parameters. Khushi, we took weight is equal to 1 because we wanted that, like, if at least one of them is 1, then we wanted to make the final output as 0. So like if we take weight 1 over here and we want to make the value that is getting inside this as 0, then we have to subtract the similar quantity from it. That's why we assigned minus weight over here, so that we get 0 over here, and then when we threshold it, we get 0 as our answer. Okay. Now in the next question, we are being asked to, like, how do we represent OR function? Okay. So I'll just give you what an OR function is. Okay. So if you have at least one of them is 1, then you get 1. Otherwise, you get 0. So it is just the opposite of the sort of AND function. Yeah, not opposite, but like intuitively. So how do you learn the weights? You can try and tell me the answer in the chat box. You can attempt this question. Akshay says it's A. I have to see what it is. So others can also try. I'll also think what it is.
A, option A.
Yeah, I also think it's option A, because if we have if we have made W2 to be 0, then if either one of them is 1, then we'll give a positive value over here, which is 1 or greater than 1. So then we'll get output as 1. So this is how a perceptron works, but it has many limitations. Okay. So one limitation, as I mentioned, is that it cannot give you non-linear decision boundary. It can approximate, but not a very good approximation. So cannot give non-linear decision boundary. Okay. So for example, this is an XOR function. So for XOR function, if you want to differentiate, separate these two using single layer perceptron, you can never get the values of W1, W2, and W0, so that you can separate these kind of points, because they are not separable linearly. Okay. So what can we do is, we can include more than one neurons now. Okay. So over here, so this is one of my neurons. So this is similar to what we had earlier. Okay. So what we had is, we had two entries, X1, X2, and then we had a connection from X1, X2 to this first neuron. This thing that I'm highlighting in yellow is my second neuron. Okay. And whatever outputs I'm getting from these two neurons, I'm again passing it to a third neuron. So this network that I have created has 3 neurons in it. So it is multiple. So I'm using multiple neurons, and also there are multiple layers. This is an input layer. Okay. This is first layer of this my network, and this is the output layer. So there are multiple layers. So also this is called as multi-layer perceptron. Okay. So just to save time here, because we have a lot to cover, So these weights that I have assigned over here, using this structure, we are able to mimic the XOR function. Okay. So this one thing is true, that this multi-layer perceptron is much more powerful than a single layer perceptron. And also to mention, like if you have a single layer, like single hidden layer, and you allow arbitrary number of neurons in this layer, then you can approximate almost any continuous bounded function. Okay. And if you have two layers, then you can approximate any sort of function. Okay. So this is the power of deep learning, why this is becoming very powerful, because it can sort of approximate any function. So just to mention, the idea that I used over here was that XOR function is a b prime plus b prime a. This is negation, or I am calling it prime. So for the first neuron, I tried to
It is bar actually. Bar AB bar plus B bar A.
yes. So this is the negation of this. So if your b is true, then b bar would be false, and vice versa. So Akshay is saying referring neuron to perceptron or vice versa is fine, right? I mean, both terms are interchangeable. Yeah, so a neuron is same as a perceptron, yes. Okay. So now coming to multi-layer perceptron, what it looks like is you have some input layer similar to what we had over here. Yeah,
Sorry to interrupt,
yeah,
Pintu Kumar.
yeah,
XOR you equated to AB bar plus B bar A means
yeah.
if we are adding the hidden layer, it is possible to combine? It is possible to do the XOR operation, right?
Yes, it is possible. What I'm doing over here is, so this first neuron, I'm trying to mimic AB bar. If you look that I'm taking -1 sign, so whatever I would have, like if it would have 1, then it will give negation of that. Okay, so this over here, I'm trying to mimic AB bar, and in the downward, I'm trying to make B bar A. Okay, and then I'm combining them as a sum. So this 1 would give us the OR function. Okay. So this is what I'm trying to do. Yeah. So this is able to like give you the XOR function. And not only XOR, but this kind of multi-layer perceptron can approximate any continuous bounded function if you allow like appropriate number of neurons in this layer. Okay, so
Previously in the single layer perceptron, you added the bias value with the weight value, but here you are not multiplying with the bias value with the weight value.
okay, so I have mentioned the bias value, but it turned out that my bias turned out to be 0. So in some other examples, there is a possibility that this bias becomes non-zero. But for XOR with bias 0 also, my problem was solved. So like bias can be 0 also, it can be some other value also. In this example, it turned out that bias was 0.
Bias is 0 as well as the weight you are multiplying is not considered here. Weight for bias multiplication.
Like
BW.
No, I'll do that. So like if you are passing it over here, but B2 is 1 everywhere. So it would be passed because its weight is 0. That's why I'm not considering it during calculation. So if you will multiply this thing with 0, it will become 0 and would contribute nothing to it.
Here the input layer is linear, output
Yeah.
layer is also linear, and the middle layer is which kind of functionality we are getting? Non-linear or what?
So for in every of the layer, in this hidden layer also and this output layer also, I'm thresholding it at 0. So like if it is greater than 0, then I'll outputting it 1. If it is less than equal to 0, so if it is less than equal to 0, then I'm outputting 0 out of this. So this is my activation function. This is called the step activation, you can call it, or 0, 1 activation or something like that. So I'm thresholding it at 0.
Okay. Thank you.
Okay, same was the case like in every example that we discussed. Okay. Now coming to the like a generic framework of a neural network. So we have some input layers, okay, which is then connected to almost, so this is fully connected feed forward neural network. So every neuron is connected to like every neuron in the next layer, okay, and we'll have associated weight with them. Also, we will have some activation function for this, and this activation function can vary from neuron to neuron. So it is not necessary that every neuron has the same activation function. We can have a different activation function for different neurons. Okay. So this is a generic network. So whatever you will pass will be processed in some form, will reach here. Then it will again reach to some layer over here. then it will again reach to somewhere over here. So because of many layers, we are able to approximate almost any function. Okay. So here is a more simpler example, like what things you have to learn. So you will have to learn these weights. Okay, there will also be some bias term over here. So that bias weight also you will have to learn. There will be some bias over here also. Okay. So these are the things that you have to learn in this thing. Okay. And how do you learn? I'll come to that. But just to mention one more thing, that like the data flows in like one direction only in feed forward neural network. So you don't have any back connections over here. And these kind of connections are also possible. So there is a framework called recurrent neural network that ma'am covered towards the very end. So those kind of things are possible, but in many applications, only our simple feed forward neural network serves the purpose. And this can would be covered in some deep learning courses and not probably in machine learning. Okay. So now, like how a back propagation work, I'll just try to give you an idea how it works. For detail, like Manak is covering it. I'll just give you a brief idea.
Propagation is only applicable in RNN only.
No, back propagation is used to learn any kind of like neural network, most kind of neural networks. So back propagation helps. What back propagation is, I'll tell you, then you'll appreciate that it can be like
You just
applied.
told us something about RNN that I want to clarify that.
Okay,
Just
what I mentioned about RNN is like in your feed forward neural network, you say the arrows are going in forward direction only. So from layer 0, you are moving to layer 1. Then from there, you'll move to layer 2 and so on. Okay. What happens in RNN is you can also have back connections. So let's say from hidden like layer n, you can have a connection back towards the layer n minus 1 again. Okay. With some appropriate weight. So this kind of network are recurrent neural network. So you can have connections. You can also have skipped connection in some kind of model. So if you are in layer 1, you need not connect this to layer 2. You can directly connect it to layer 3. So these kind of modifications are possible. But right now what we are covering is like a fully connected feed forward neural network. I hope I'm clear.
Thank you so much.
Okay. So now like we want to learn these weights. Okay. Now to update these weights, we again use our gradient descent method, that is like the same for linear regression or logistic regression that you did. Okay. Now let's say there is some error function defined over here, and you want to differentiate with respect to, let's say, this weight 211 or weight 311, then like how do you differentiate it is not straightforward. Okay. So how do we find the gradient with respect to these things? So partial derivative with respect to this thing, that algorithm is called something as backpropagation. Okay. I'll give you an example. Let's say we have a function f of g of h of x. Okay. And then you want to differentiate this function like thing with respect to let's say you want to do something like this. I'm mentioning this partial symbol on purpose because over here all the derivatives would be partial only. That's why, though this is a function of only one variable, I'm using partial symbol only. Okay. So what you would get is you would get something like f dash of g of h of x. Okay. Then multiplied it with g dash of h of x. Then multiplied it with h dash of x. Writing it in other form, you will get something like del f by del g into del g by del h, and then del h by del x. So this is something called the chain rule that we get. So back propagation also works on the same principle, that is your chain rule. So you have some error function. Okay. Now this error function would be based on this, let's say this is output of layer 3. Okay, so this would be output of layer 3 and minus your, let's say, y, whichever was. Let's say we are talking about regression right now. So we'll have something like this. Okay. Now this output thing of layer 3 will be based on the activation function of this phi L3, right? So this can again be replaced as like phi of your some summation like w1 I I is equal to 1 to 2. I'm just taking this example as my reference. Okay. And some this activation again, which is your phi of L, like L21. So what I'm doing here is, I'll just say what I'm doing. What I'm doing is, so this output of L3 can be replaced by this activation of this neuron. Okay. And what is the input to this neuron? This is whatever is the activation of this times W11 and activation of this neuron times W12. Okay. This is what I'm trying to mention over here. Again, if you will, again, if you want to now differentiate with respect to W11, you can take this, sorry, you can take partial derivative of this del E by W11, or let's say W22 of 2 with respect to this parameter, okay, or with respect to this parameter, let's say W12 of 2, by differentiating this partially using chain rule. Okay. Now, as you move backwards, this like equation will start becoming more complex. But if you look at this carefully, that this W2 partial derivative will depend directly on partial derivative of this component. So calculating this partial derivative with respect to this one directly incorporates this partial derivative with respect to this activation function. So that's why this thing is called backpropagation, because we want to calculate the, I'll change the color. We want to calculate the partial derivative first with respect to this, then we move with respect to this, so that we are able to use this information. Then we move backwards, so that we are able to use again this information. And this Manak will cover in detail, like what is the exact formula and those kind of things. But the basic idea is that you will have chain rule being used to calculate the partial derivative to update the parameters. Okay.
Pinto Kumar, sir, actually, I am not getting that how the backpropagation as well as in RN, if you talk about the RNN, how the backward or feedback links are working.
Okay. First, I'll mention something about RNN, then I'll try to come to backpropagation. Okay. Now, let's say you have two neurons in the input layer. Okay. And there are two layers. Okay. And there is some output. Okay. How would a feed forward neural network look like? It will be connected to every neuron in the next layer. So something like this, and then again like something like this, and then this being connected to this. This is how a normal feed forward neural network looks. Okay, now RNN is not exactly like how I'm mentioning, but I'm telling you how back connection can be. Like in RNN, what happens is, let's say RNN, I'll just tell you first what an RNN is. RNN is used in natural language processing. So if you have, let's say, some word like I am hungry, okay, and you want to translate it or do some computation on these kind of things, then if you want to pass this like to this to a neural network, then you have certain order associated in it. Okay, then what happens, while passing this complete statement to a neural network, we have some connection between these words also. Okay, so these can be viewed as back connections. I'll say what a back connection is now. So let's say like all these like the sky blue arrows that you're seeing are in forward direction. So when you input some entry, then the information will flow in this forward direction only. Okay. What happens in RNN is, from this layer you can again have one more connection that is in backward direction. So whatever information that you learned over here can be again fed into the earlier information, and then again it can be passed further ahead. Okay. Now let's say you want to learn a translation for I am hungry. Then if you look at like translations, then words are related to each other. Okay. So whatever you learned, so like some words have like context based on the words around them. Okay. Like mm, I'll give you an example how that thing can vary. Okay, so
If it is not
you
clear, we can move ahead.
just wait a minute. You are a boy is a sentence. Okay. Another word are you people are intelligent. Okay. Let's say you want to translate these two sentences. Okay. Now, over here, R is like, if you look at R over here, this is talking about just a one person. So if you want to translate into some language like Sanskrit, where you have like different words for different like one person, two person, and ekvachan, bahuvachan, and dvivachan, you have something like that. So the meaning of R would vary at both these places, right? That thing you should agree, like R is different for in both these sentences, like used at different places. So what happens in a sentence is like a same word can have different meaning based on the context or the word around it. How to capture that thing via neural network is like if you will pass just R, let's say you learn some weight and then you are passing R from throughout the network without any back connection, you will get the same output. Okay. If you have same input, you should get the same output. Also, if you have a simple feed forward neural network. But when we want to learn from the things around it, so let's say this layer in your sentence is learning about the third word in the sentence. So this layer, whatever you are learning in this layer, is responsible for third word in the sentence. Then you want to pass on this information to the second layer. Like when you first pass the word you, okay, that is fine. You pass the word you over here. Then you passed R over here. Okay. Now you want to also incorporate information about the words neighboring. So you first learned about what could be a possible translation for R. Then you learned what is the possible translation for people. Based on whatever the translation for people was, then you try to again learn what was learn or update whatever you learned about the word R. So these kind of thing, what you're doing is you are again feeding extra information that you learn in the later stage to the stage that you learned before. So this kind of thing is something called a recurrent neural network. Am I clear now?
Sir, thank you.
Okay. Okay, so Akshay is asking backpropagation. No, Akshay, what backpropagation does is, so backpropagation is used to find the appropriate weights. So you will have some random weights, okay? You will have some very random weights to begin with. Like in linear regression also you had like summation, you remember xi, wi. Then these wi's you had to learn using gradient descent, okay? Similarly, like over here also you have like weights that you initialize randomly initially, but later on you learn the appropriate weight so that it can fit to your data. So this is what we want to do. So we want to learn some appropriate weights. This is what we are trying to do over here. So by a backpropagation, we find the gradient. If you remember, how do we update our weights is W minus some alpha times gradient of error function. Okay. Now this, like if you split it, so Wi is equal to Wi minus alpha del E by del Wi. How to calculate this del E by del Wi is given by your backpropagation algorithm. Okay. And that is done via chain rule. This is what I am saying. Okay. So I have included a resource over here. Manak is also covering, but I have included a resource also over here. If you just go to this link after I post this thing, there is like a solved example for backpropagation, that too step by step. So you can have a look onto it. Like if those things
Could
are
you
not.
go? Could you go over that, or shall we ask to Maina for that? Moina,
Manak won't, I think, cover that link. Okay, but like you can, I'll go to that
if you
link.
can, if you can
Sure, sure,
quickly go on, yes, then
sure. I'll go.
yes. what the Moinak is doing is translating everything in maths.
Okay. So yeah. So what happens over here is, so there is a forward pass, I think would be clear to you. I'm probably using some website, but I'm sure. Okay, it's fine. Like this forward pass should be clear to you. I won't be able to write on this screen. I don't have any option to write over. Yeah. So let's say you had this neural network to learn. Okay. So you can see there are weights. There is a hidden layer. There is an output layer. Initially, you can initialize any weight to it. Okay. So he randomly throw some weight and like weight to bias as well as this W1 to W8. And then he did some forward pass. So he had a data point. Let's say he would have mentioned what's the data point that he's using. Uh, okay. So he's like using this specific, so this, I'll see, this is 0.15 and this is 0.25. What is he using? So this is what he's using. So 0.05 and 0.1 is the initial, yeah, he has mentioned over here also, sorry. 0.5 and 0.1 is the initial data point that is passing over here. Based on that, he has calculated some error over here, and his activation functions over here are sigmoid activation function. That I'll cover in a minute. Okay. Now he has calculated the total error, or because he had only one data points, he has calculated the error. Now how do we go to this like update of weight? That's what he is like. I think I'll just do one thing. Just wait a minute. Just give me a minute. I'll just copy his network. Just give me a second. Just give me a minute. Okay. I'll do it. Okay, and then
Pintu sir, Pintu Kumar sir, actually, it is a very time-consuming process to learn the back propagation. Could you explain this in some other session, because you can carry on with your current stuff, and we can discuss these things in some other time later
that
on.
I agree. That's why I sort of skipped this topic because that would have taken the
It's
complete lecture, and I wanted to cover other things that was probably
Can you
not covered in the lecture.
we will join at the 8 o'clock. Could you proceed with that at 8 o'clock?
I can do,
This
but I just give me a minute. I'll try to give you an overview at least because I have copied it. I'll try to give you an overview and then we can move forward. Give me a minute. Just give me a Windows. I think now this thing should be visible. Okay. Now I will be able to at least write on this. So that's why I sort of copied everything. Yeah. So what he's trying to do is he's trying to find the updated like weight, how to update weight for the weight W5. Okay. So error over here, we have two output layers. Okay. We have layer 1 and this output 1 and output 2. So the total error that you would get is error from output 1 plus error from output 2. So these both the two things would be contributing to your error in this case. Okay. That's why. So if you have this like if you are trying to differentiate this with respect to W5, this total error, now this error, if you will see, is equal to your error of output 1 plus error of output 2. Okay. So if you differentiate this with respect to W5, what you will get? You will get error of output 1 by 5 plus error of output 2 by W5. Now if you look carefully, this was also a function, but because this was summation, we could easily split it. So this is what he has also done. So he will get summation somewhere. Okay. Now, if you look at this O2, in O2 we don't have a dependence on W5 parameter. So when we will do chain rule and we'll do more derivative, this term would probably go to 0. Okay. Now the main thing is with respect to this, I'll just try to like find the exact formula for this one at least. So what we are trying to do is we want to find the error due to O1 divided by this partial derivative with respect to W5. Okay. What we want to do is what this error would be. So this is, let's say, something like output 1 minus y whole square. Okay. So if we want to find its derivative, what it would be? It would be 2 times O1 minus y, okay, into del O1 by del W5. Is this thing clear? Like the way you used to do differentiation in your childhood. So this term was not dependent on W5, so we didn't took its derivative. This term was dependent, so we again multiplied it with derivative with respect to W5. Okay. Now when we try to do this thing, this O1 is dependent on 2 parameters. Okay. What it is? H1 W5, look carefully. This is H1 W5 into H2 W6. H2 W6. Now, if you take its derivative with respect to W5, what do you get? You get H1. So now, what partial derivative you would have got is O1 minus y into H1, I guess it is, yeah. Right. So this is your partial derivative with respect to W5. Similarly, you will find it for every value from W1 to W5. Append it in a vector called W, this gradient of W. Okay. And then update the weight accordingly. So this is the basic idea behind this. Like if my next thing is also not clear, you can you have this discussion forum, right? You can post it over there. I'll try to post some content, even if it is that not clear, we can have this back propagation specifically covered in some other session.
But where did we apply chain rule in the example that you were doing just? I mean, it's
Over here,
simply
this O1 was dependent on your W again. So
this was a chain rule. Okay,
here where
okay.
we applied the chain rule. When you will have deeper networks, and if you, let's say, wanted to do it with respect to W1, then again this H1 would
O1
also
will.
be, yeah,
Mhm.
H1 would
Got
also be differentiated with respect to
Okay.
W1. So this is how this chain rule proceeds.
Okay.
Now, one thing that I wanted to mention, which is important from application point of view, is how do you decide upon the output layer? Like how many neurons should be there in the output layer? What should be their activation function? So one thing that I personally use is that it is based on your, I think, just a second. My screen is not functioning, just a second. Some issue with the screen.
Pintu Kumar, sir.
Yeah, just, can you please check?
Sir, we appreciate your sessions and we really like your sessions too. We are getting something out of it. Could you please engage this back propagation with more clarification and all this, because
Sure.
we don't have any background knowledge about what is chain rule and why it is required and how it is applied, all these things.
Okay, I'll try to do it. So,
Please.
sure, I'll try to do it. Okay, so now coming back to what we were doing. Okay, so I'll do this. I'll post like a specific time probably, or probably I'll record a session and then post it and post the link in the that chat. That thing would be okay, or you want a live session?
We want live sessions.
Okay,
We
I'll
want,
arrange. I'll arrange. Probably not today, but I'll arrange.
yes, please.
Okay. So now coming back to this output layer. Okay. What we have in our output layer is like how to decide like what should be our output layer. Okay. Just give me a second. Yeah. So I prefer to like the thumb rule is to decide it based on the task that we have at hand. So if you look at the common machine learning tasks, they are regression and classification. Okay. Now in regression, in classification again you can have binary classification, you can have multi-class classification, and you can have multi-label classification also. Okay. And all these things, like if you remember logistic regression, so for multi-class and multi-level case, you had to train one logistic regression function for every class. So you had 10 models to train over there. Okay. Advantage of using neural network is that you can do it with the help of just one neural network. So for example, this network that they had drawn, so the output one could give you the prediction for class 1. This output 2 could have given you prediction for class 3. If you had one more neuron, so that would have given you prediction for class 3. So in a single go, you can learn from which class this belongs. Okay. So now coming back to what I was saying is, so if you have a regression problem at hand, so in regression, what you want is your final output should be a real number. Okay. In regression, what you try to do, for example, for house prediction data, based on the feature of house, you want to predict what should be the price of the house. Okay. So what is the final output that you want? This is a real number. So now if you have a real number with you, so what kind of output you want? You would want a single output. Okay. What activation function to use, that I'll come to in a minute or so. I'll cover it today. Okay. Now coming to the binary classification. For binary classification also, you can have a single output neuron. Okay. So like if the output is greater than, let's say, 0, then you can predict 1. If it is less than 0, you can predict -1 or 0, whatever the way you are comfortable with. So you can have a single output layer, but its value should be between some fixed range. So it should be between, let's say, -1 to 1 or 0 to 1, so that you can decide on the labels that you want to give to it. Okay. Now, if you move to multi-class classification, then your output layer should have like number of neurons equal to number of classes that you have. So if this is your output layer, okay. So let's say we have 4 classes. So you want to know if it is a flower or a dog or a cat or some other class. So you would want 4 different classes. Okay. And based on whichever output is maximum, you can predict that class. Okay. Now, this 4 output should again be between some fixed value, so that you can compare these things, like which is greater, which is less. So it can be something between, let's say, -1 to 1 or 0 to 1. So what kind of values we want, based on that we'll fix our activation function, that I'll cover in a while. Now coming back to a assignment problem that was given, it asks you like this non-linearity in a neural network is because of what thing? So this says that it is due to gradient descent or bias or sort of the activation functions that you use, or none. So if you remember linear regression, yeah.
I think it is bias answer.
No. So like if you remember linear regression, there also you use gradient descent. There also you use bias. So these two things are common in these two things. So linear regression was your just a linear model. So that is not the reason. So your non-linearity comes due to probably two main reasons.
Gradient we are using in logistic, no?
Gradient, yeah. In logistic also you use, and in logistic also, if you are not using any transformation, then again it's just your linear thing only, right? You get a linear decision boundary only in logistic regression also. So your nonlinearity arises due to two reasons. First is your choice of activation function. Okay. And next is because your network is complex. So this is because of the multiple layers of network. Again, even if you have just the multiple layers without any activation function, you will get a combination of linear things only. So this activation function, not only ReLU, any other activation function also plays important role in making it non-linear classifier. Okay,
It
so
must be in the hidden layer only, right?
activation can be in hidden layer as well as
Layer
in the
only.
output layer.
Output layer also. Okay.
Yeah, hidden as well as output.
Okay. So due to the activation function, non-linearity exists in neural network, right?
Yeah. And
Okay. Okay.
output function, like what kind of output layer you should choose, that I discussed. Now, this question asks you is like for a fully connected deep network with only one hidden layer. So you have this, and you have one hidden layer over here, and you have some output. Increasing the number of hidden units. So in this, you are increasing the number of neurons or the perceptrons that you have. Like, what would it lead to? Okay. Now, if you have a high number of neurons in the hidden layer, what it is doing, it is increasing the model complexity. So with increasing model complexity, what you get? You get increased variance and decreased bias. So A option would be the correct option for this. Again, I think this question we have already answered. So you are given a task of predicting house, okay, given some features. How many neurons should you have at the output? So at the output, you just want the price of the house, right? So how many neurons you expect? You expect only one neuron
One.
in the output.
Because we are going to convert it into again
Yeah.
in the class, no, multi-class.
No, no,
No,
no.
single class.
So here you don't want the class, you just want the price of the house. So what should be the price? Exact price.
It is the price actually. It is a continuous value, but the
Yeah.
neural network never gives the continuous value. No? Yes.
Neural network can give you a continuous value based on the choice
Okay.
of your
Okay.
activation function in the output layer. Okay, it can give you continuous value. So
Continuous value. Which activation function is used?
you can use linear. There are common. So I'm coming to them. But I'll mention because you asked. So you can use linear activation function. You can use ReLU. You can use leaky ReLU. Okay, these sort of gives you continuous valued outputs. Okay.
Great.
So now, I'll just cover some famous activation functions and their advantages and disadvantages, so that when you implement these kind of things, it's useful to you. And one more thing to mention, like even if you don't get a theory behind backprop, okay, theory behind the backpropagation, it is useful. It is an important theory, but if you don't understand it, so using PyTorch, you can implement it even without knowledge of like exact formulation of backpropagation. PyTorch take care of this on their own. So if you will call this gradient function, they will calculate the this backpropagation gradient on their own. You did not specify the exact formula for that. Okay. So because of these advancement only, this neural network became this popular that you can easily train it without getting into the exact maths of it. So the first activation function over here is your linear activation function. Okay. So this is a very simple. So whatever you are getting, so this x, always remember that x will be always a form sum wi summation, right? This is what we pass to activation function. So if you look at the neuron, so there were some input x1, x2, x3, and then you took their weighted sum and then passed it to some activation function. So I'm talking about this activation function. Before that, we have taken their weighted sum, and I'm just talking about the activation functions right now. So first is linear. Whatever sum you got, you just pass this on. Okay. So this kind of things is useful in your regression task and those kind of things. When you don't want a lot of non-linearity or model complexity in your network. Second and important one is your sigmoid activation function. This you have encountered in also in your logistic regression. So this is given by 1 upon 1 plus e to the power minus x. Now, though I was not able to explain you clearly what backpropagation is, I'll mention one thing. Let's say you have 10 hidden units. I'll mention, just believe me that this is true. There are 10 hidden units. Okay. Now, if you are trying to calculate the error of your with respect to the weights in first unit. Okay. So this will have like many terms in it. So multiplication of many gradients. So this with respect to probably output of second layer, and then this output of second layer with respect to E1. Okay. W1. This output of second layer will again have many terms. So there are at least, let's say, 15 terms involved in this multiplication, 15 different gradients with respect to different terms that you will have over here. So because if you have gradients very small, let's say over here, this is this pink or the purple line is for your derivative of this function. And you see it is just between 0 to 0 0.5, 0 0.25. So if you have multiplication of these small numbers, this gradient sometimes becomes very small. Okay. So when your gradients become very small and you are trying to update your weights, something like this gradient of W, because this value is very small, your change in weight is very small. So your weight is actually not changing a lot. This phenomena is called vanishing gradient. Okay. So you are not learning anything out of it. So you won't learn using these data points when you are encountering vanishing gradient. Okay. So another related formula is this phenomena is exploding gradient that would occur in something like this phi of x is equal to x. So if your x value is in thousands or something like that, that is very much possible. So this product kind of explodes a lot and your W starts changing very much. You're getting very large Ws and those kind of things. So both these phenomena we want to avoid. So linear, though, is very simple calculation wise and everything, but because of exploding gradient, many people don't use it in like practicality. And sigmoid also, I have mentioned the advantages and disadvantages, but I'll mention the main disadvantage, which is that it will suffer vanishing gradient. Like if you have very deep network, then you will suffer vanishing gradient if you're using sigmoid kind of activation function. Also, this is not a zero-centric function. So if you look at its value that it is taking between 0 to 1. So it is always taking positive value. Okay. If you want to like combine this with some, let's say, step function kind of activation function, then it will always give you positive value. So for step function, if you remember, if it is greater than 0, then you will predicting 1. So this always gives you positive value. So it like if you are composing it with some step function, then whatever output you will get will always be positive. So we try to like make a combination of all zero-centric functions so that these kind of phenomena do not occur. So these are two main disadvantages of your sigmoid activation function. There are many advantages also, like it is a very smooth function and differential everywhere. It is between 0 to 1, and so hence it is very useful in binary classification kind of tasks. Okay. So to cover up some of the disadvantages of your sigmoid activation function, we move to a function called tan H activation function, whose formula is given by this. So it is able to solve one problem of your sigmoid activation function, which was that it is not zero-centric. This blue curve is your function for tan H function. If you see carefully, its value is between both minus 1 to 1 rather than 0 to 1. If you look at the shape of both this curve, this is sigmoid and this is also your tan H. So your sigmoid was between 0 to 1, and in tan H you have similar shape between minus 1 to 1. So we are sort of just scaling it properly. This is zero-centric, this is its advantage. And if you look at its gradient also, this is like going up to 1. Though it is going up to 1, it is solving this gradient vanishing problem to a large extent. So it is performing much better than your sigmoid function. But still, in some cases, if you have very deep networks, then it sort of suffers from your vanishing gradient. So one option is to, in your hidden layers, use some other kind of activation function, and only in your output layer, if you use tan H or sigmoid, then that kinds of become very useful. Okay. So what kind of function activation function you should use to avoid your vanishing gradient? One example is your ReLU function. So this blue is the graph, so it will extend over here also. So till if your value of x is less than 0, then this value of ReLU function is 0 if you look carefully. And if it is greater than 0, then it is given by x. So this is something called the ReLU function. This can also be denoted by your max of x comma 0. Okay. It is not differentiable at 0. This is a like drawback, but you kind of use its pseudo derivative. So you can either use 0 as its derivative or something like that. Okay, or you can use like a very small quantity as its derivative, because 0 might lead to some other issues. Now one more thing, this both of the sigmoid and tan H had exponential in them. So calculating exponential value is sort of computationally expensive also. So this ReLU has covered that problem also for us, so that this computation is also very inexpensive over here. It does not suffer vanishing gradient. Okay. And it is very useful in regression tasks. It can be used as output layers for regression tasks. And for classification task also, it is very useful as a hidden layer units. In output layer, you can use sigmoid or tan H. In the hidden layer, you can use your this kind of activation. Again, the disadvantage is that it is not a zero-centric function. Okay. There is a problem called dying ReLU problem that I want to mention. Okay. Now, for values less than 0, the value of activation function is 0. Again, I have not covered in detail backpropagation that I should have, but yeah, like if you will look at the derivative with respect to initial layers, uh, so with respect to initial layers, you will have some terms like output of some layers ahead of it. Okay, you will have these terms in that multiplication. Now, because when your x is less than 0, the ReLU function is outputting value as 0. So this output sometimes becomes 0, and it leads to some of these like derivatives being 0. So let's say your network is something like this. Okay, so let's say there is only one input and there is some output. Okay, so if this term becomes 0, then this weight, because this weight is related to activation function via this neuron, so this derivative also becomes 0, partial derivative. And because of which this weight does not get updated by that specific data point or that batch of data point, if you're looking at batch gradient descent or those kind of things. So this problem is called the dying ReLU problem, that it does not update many of the like weights. It updates the weight only for which you are getting non-zero values throughout the path. Okay. So this is one thing. To overcome this, we have a variant of it called leaky ReLU function. In this, rather than choosing 0, we take a very small a and we take ax over here. Okay. So we take a very small negative value. So by this way, we avoid this 0 thing. So it solves your dying ReLU problem. But it now comes up with a new problem, which is like, how do you fix this a? So fixing this hyperparameter a is not very easy. Okay. So yeah, so this is like modification for leaky ReLU, but yeah, it comes up with another problem. To cover the last one, this is something called softmax activation function. Okay, so this is mainly used in multi-class classification. So let's say you had a neural network, I'm just denoting it by, and your output layer is some 4 classes. Okay, and the activation function that you have till now is, let's say, some ReLU or these kind of things. What you want to do is you want to convert all these values to some probability. What is the probability of class 1? What is the probability of class 2? Okay, you want to do something like this. Then what you do is you use softmax activation. So I'll just mention something. So if you have, let's say, some 5 data points, this is 5, 6, 7, 8, 9, 10. These are the value associated with something, and you want to convert it to probability. So what you want is like these values should be converted to something between 0 to 1, so that their sum is also 1. Okay, this is what you want. So one way to do that is your softmax activation function. So you can calculate e to the power zi divided by summation of e to the power zk. Okay, so this way you would be able to convert every of these values to probabilities. Okay. So one disadvantage that is very prominent disadvantage is that it has summation of exponential in the denominator. Okay, and when you have large number of classes, then this summation calculation is computationally very expensive. So this sometimes becomes an issue, but yeah, still it is very useful. Okay, so I'll cover these two questions. So question 6 is this housing prediction problem that we had. So you have some features related to some house given. You have to predict the house. This is your question 6. Okay. Now these two questions over here are related to this only. Which of the following activation function should be used in the output layer of the question 6? So this is a regression problem, right? So sigmoid is useful in binary classification. Softmax is used in multi-class classification. And ReLU is useful for your regression in your output layer. Okay, so option B is correct. What is the loss function that you should train? So you have some y predicted and some y original, and you are solving a regression problem. So mean squared error is the best option. Multi-class class entropy is for multi-class classification. Binary cross entropy is for binary classification. Okay. I have included some resources over here. So the first one is again one more resource for backpropagation. I would request to go through them first. I'm almost 90% sure you'll get what backpropagation is after looking at this, because they have some illustrative diagram and those kind of things. And I also have some resources on CNN and autoencoder that I find are useful, and you can have a look onto them and get an idea what these things are. Again, for detailed thing, 1 hour thing is not a lot. Even one semester is very small to learn everything about deep learning. So if somebody is interested, you should do a full course on deep learning, probably via NPTEL or any other resource that you like. Any other doubts that you have?
So just one, like in a neural network, nodes are like just classes, right? Or the features of classes. Like what does node represent in the
Okay.
neural network?
Oh, okay. I'll see. So I am drawing a neural network. Okay. I'm drawing a simple one. I'll make it more simple. Let's say we have 2, 2, and 1. Okay.
Hmm.
So first tell me which node are you asking about, this layer nodes or this layer nodes or this layer nodes?
So the first one, left side would be input node, middle
This
would
is
be
input.
hidden, right would be
Yeah.
output.
Yeah. This
So
is input
in,
node.
yeah, so
Tell me.
input might contain the class labels or depend on data set. So what does this hidden layer node represent?
Okay. So your input node that you have would be so if you remember linear regression, your basic data is of form xi comma yi, right?
Yeah.
So your xi's are your features corresponding to your data set. Okay. So what you give in input are these features that you have learned. So let's say for
Yeah.
a house prediction, this can be your square, the area of your house, or those kind of things. Okay. And your yi would be useful later on while evaluating the loss function. Now in your hidden layer, these are the hidden representation that a neural network learns on its own. So what does this represent is a very important but unanswered question. That's why you would have heard that these neural networks are sometimes called as black box, because these representations are learned by this neural network on their own. They use these to find the proper output, but why are they learning this specific representation? That is not explainable right now. That's why we call neural networks as non-explainable. So these are some intermediate representation that a neural network sort of learns on their own. Let's say we are looking at a house in terms of prices and those kind of things. This is its own understanding of how to calculate a price, that I would say. This is what they represent in a hidden unit. So let's say there is an image of let's say a tree. Okay. So you pass an image, then in the first hidden layer, a neural network, what might he want to learn is he might save some boundary for that thing. You want to extract the boundary out of it and store boundary. It might or might not store exactly the boundary, but I'm just giving an example. he might store the colors that are in that picture. So this is what he might store in intermediate hidden layers. But when you sort of try to visualize it, they store some very random things which is not explainable, like what are they doing and how they do.
So while calculating the price of a house, we have area, we have location, several other parameters. Those are classes, right? Whatever
Those are
the
your
data sets are there, those are features.
see the area that see there are like if you look at machine learning regime as a whole, there are many kind of tasks, but broadly there are two kind of tasks. One is regression, okay. One is classification. So in regression, what you want to do is, so your features is not something that are your classes. Your features can be categorical. So let's say,
Yeah.
let's say for a house, okay. So you can have like number of rooms as 1, 2, 3, 4, which you can see as if they are classes, okay. But they are your features and not the classes that you want to predict, okay. So these are the features that you have in your data set. Using this, you want to learn some continuous value. Let's say price. So price is not categorical or classical. Like it is not divided into class that you can see. So those kind of things falls into regime of regression. So there we don't talk about what are the classes and
Yeah.
those kind of things. Classes we talk when we are about.
Okay.
Yeah.
Got it.
Okay.
Okay, fine.
Anybody else?
Sir, what is the difference between clustering and clusters?